This research paper delves into the phenomenon of current-induced spin accumulation in chiral topological semimetals, a rapidly evolving field due to its fundamental and applied interest. The paper centers on the property of spin momentum locking, which is a result of Weyl nodes acting as sources and sinks of the Berry curvature. In 3D Weyl semimetals, band-touching nodes always come in pairs of opposite chirality, but when these nodes have to appear at the same energy due to crystalline symmetry, the spin accumulation in response to a charge current cancels out between the two nodes in any given pair. However, when inversion and mirror symmetries are broken and the opposite chirality nodes appear at different energies, spin accumulation becomes possible. The authors develop a theory of current-induced spin accumulation in chiral topological semimetals using a simple toy model of a pair of opposite chirality Weyl nodes, separated in both energy and momentum, and taking impurity scattering into account. They derive a set of coupled spin-charge diffusion equations, which describe the intertwined transport of non-equilibrium spin and charge densities in a generic chiral semimetal. The spin accumulation in response to a charge current in such semimetals has a non-trivial non-monotonic dependence on the Fermi energy. The maximum spin accumulation, h(2 per electron), is achieved when the Fermi energy coincides with the location of one of the nodes and decays away from this value. Additionally, the authors demonstrate a closely related magnetoresistance effect, where spin injection from a ferromagnetic contact leads to an extra contribution to the voltage drop, which depends on the orientation of the magnetization of the ferromagnetic contact relative to the current. This paper provides insights into the properties of chiral semimetals and their potential applications in spintronics and other fields. The research paper delves into the transport phenomena in chiral semimetals, materials characterized by a unique band structure featuring pairs of Weyl nodes separated in momentum and energy. The authors employ a Hamiltonian model that includes impurity scattering to describe the system's behavior. This model introduces two bands that touch at Weyl nodes, separated by an energy gap of 2 increment and a wave vector of 2q. Impurity scattering is accounted for using the standard diagrammatic perturbation theory, specifically the self-consistent Born approximation, SCBA, and ladder vertex corrections. This approach allows for the evaluation of the impurity average Green's function, crucial for calculating the density and spin density response functions. The authors then derive the transport equations using the retarded density matrix response function, which describes the system's response to external fields. This function is evaluated using SCBA and ladder vertex corrections, assuming that the quasi-particle energy near each Weyl node exceeds the scattering rate. However, this approximation breaks down when the Fermi energy approaches one of the nodes, as the scattering rate remains finite due to internode scattering. Despite this limitation, the results obtained from this approximation are smooth functions of the Fermi energy, suggesting qualitative correctness for any value of the Fermi energy. The approach neglects quantum interference processes, which should be justified in three-dimensional systems when disorder is not too strong and temperature is not too low. In summary, the paper presents a theoretical framework for understanding transport phenomena in chiral semimetals, utilizing a Hamiltonian model that accounts for impurity scattering and employing diagrammatic perturbation theory to evaluate the response functions. The results provide insights into the behavior of these materials under various conditions, highlighting the importance of considering impurity scattering in the analysis of chiral semimetals. In chiral topological semimetals, the spin-charge coupling is a crucial aspect of transport phenomena. The authors derive the spin-charge transport equations, specifically the inverse diffusion matrix and the coupled spin-charge transport equations, in the steady-state regime. This derivation is based on the Kubo formula, which yields the spin susceptibility, chi-ab, q, omega, describing the response to an external magnetic field. The expression involves the matrix element pab, q, epsilon, epsilon plus omega, and the Fermi-Dirac distribution function, nf, epsilon. By focusing on the long wavelength, low-frequency response, the authors simplify the expression for chi-ab, q, omega, assuming that states labeled by k and k plus q belong to the same valley due to the separation of Weyl nodes in momentum space. This simplification enables the derivation of the inverse diffusion matrix, d, q, omega, which describes the coupled spin-charge transport equations. The matrix elements of d, q, omega include terms related to the diffusion constant, d, and the spin-charge coupling, gamma, determined by the product of the Fermi energy, epsilon f, and the energy gap, delta. The coupled spin-charge transport equations are solved in the steady-state regime, assuming transport in the x direction and uniformity in the y and z directions. This yields two equations describing the spatial variation of charge and spin densities, n, x, and sx, x, respectively. The first equation describes charge conservation, while the second equation describes spin relaxation, with a source term proportional to the electric current density, J, and the degree of spin polarization, Xi, at the interface with a ferromagnetic electrode. A new length scale, LCs, is introduced to characterize the strength of the spin-charge coupling, demonstrating its impact on the spin relaxation length, Ls. The authors also present a semi-infinite sample model, where electric current is injected from a ferromagnetic electrode at x equals 0, and solve the coupled spin-charge transport equations in this setup. This analysis provides insight into the interplay between spin and charge transport in chiral topological semimetals. Magnetoresistance measurement setup is illustrated in Figure 3, where current is injected from a polarized ferromagnetic electrode into a chiral semimetal sample and extracted by a normal metal electrode. The boundary condition for the spin current is given by equation 14, which includes the contribution from spin momentum locking near a Weyl node. However, this contribution does not correspond to actual transport of spin and is therefore excluded from the boundary condition. Solving equation 12 with the boundary condition 14 yields equation 15, describing the spin polarization of the charge current in the chiral semimetal. The first term in equation 15 represents the intrinsic spin polarization of the charge current, while the second term represents the extra spin density injected from the ferromagnetic electrode. The voltage at a distance Lx from the magnetic electrode in response to the injected current is given by equation 16, which includes both ohmic and non-ohmic contributions. Ohmic contribution is given by equation 17, while the non-ohmic contribution is given by equation 18. The non-ohmic contribution arises from the extra spin polarization injected from the ferromagnetic electrode and has a non-trivial scale dependence. The ratio of non-ohmic and ohmic contributions, given by equation 19, characterizes the strength of the magnetoresistance effect. Current-induced spin polarization and non-ohmic contribution to the voltage exhibit a non-monotonic dependence on the Fermi energy, vanishing at charge neutrality and far away from Weyl nodes, and reaching maximum magnitude when the Fermi energy coincides with the location of one of the nodes. Results are illustrated in Figure 4, showing bulk current-induced spin accumulation and magnetoresistance as a function of the Fermi energy. Maximum possible magnitude of the spin accumulation is normalized to unity. Non-monotonic dependence on the Fermi energy is a key feature of the results, and the ratio of non-ohmic and ohmic contributions may be used to characterize the strength of the magnetoresistance effect. Main results are given by equations 15 and 19, describing current-induced spin polarization and non-ohmic contribution to the voltage, respectively. These results may be used to understand the magnetoresistance effect in chiral semimetals and to design devices that exploit this effect. In conclusion, the theoretical analysis of current-induced spin accumulation and magnetoresistance in chiral semimetals has been presented. The non-monotonic behavior of these phenomena as a function of the Fermi energy is a key finding, with maximal effects observed when the Fermi energy aligns with the location of one of the Weyl nodes. This can be achieved in thin films of chiral semimetals such as CoC and RHSI. The research acknowledges financial support from various institutions and provides detailed calculations for the diffusion propagator in the appendices. This study contributes to our understanding of the interplay between spin, charge, and momentum in chiral semimetals, paving the way for further investigations into their potential applications in spintronics and other quantum technologies. We derived the expression for the current-current correlation function EOB, Q, omega, in the presence of disorder, as given by equation A8. This expression is a sum of pairwise products of retarded and advanced Green's functions, integrated over momentum. Following the standard procedure, we use the identity, A10, to simplify these expressions. For the specific case of gamma OO, Q, omega, which is a sum of products of retarded and advanced Green's functions, we obtain an expression in terms of the Fermi-surface integral using the identity, A10, as given by equation, A12. Evaluating this integral yields the final result for gamma OO, Q, omega, in equation, A13. We then evaluate the remaining momentum integrals in equation, A8, in a similar manner, resulting in the final results for the matrix elements of EOB, Q, omega, in equation, A14. These expressions are given in terms of the mean free path L equals VF tau and the Fermi energy EF. These expressions can be used to study diffusive ballistic crossover phenomena when OT and QL may not be assumed to be small. However, in the limit where OT and QL are small, we can expand these expressions to first order in OT and up to second order in QL, yielding the results given in equation 6 of the main text. The expressions derived in this section are based on several assumptions, including the assumption that omega, VFQ, and 1, tau are small compared to EF plus or minus increment. While this assumption breaks down when the Fermi energy approaches the location of a Weyl node, we note that the final results are smooth functions of EF and increment. The results presented in this section build on a number of previous studies, including those by Volovic, Armitage et al., Murakami, Wan et al., Burkov and Balance, Sun and Spivak, Burkov, Shang et al., Li et al., and Cheng et al. These studies have explored various aspects of topological semimetals and their transport properties, providing a foundation for the work presented in this paper. The comprehensive literature review presents an in-depth examination of related work, laying the groundwork for future investigations into Weyl and topological quantum phase materials. Relevant experiments, 1627, 29, 3334, have established crucial methods, parameter mappings, and intriguing side studies that the report elaborates on, providing proofs concerning mass-protected signals involving localized types generating inherent complex singularizations detected alike versus paramagnet nature. These are theoretically disclosed thoroughly in other subjects, which will be explored later, as they are non-destructive at temperature transition out-of-reach boundaries, strongly proposed and explained, with their crucial implications. Symmetry momentum given nature boundary limits electron information providing direction predictions expected from full interdisciplinary correlation modeling towards making advances confirmed highly nonlinear approaches relevant underlying these interactions demonstrated general states lattice experiments validated mass strong all from dynamical modulation unclassifies demonstrated theories computational dynamics taken constant by its explanations necessary developments especially valuable direction needed then under rigorous through examined on local measurement implications first clearly wide measurement field even applied giving directions generally reviewed explaining beyond clear expectations boundary across thermometric generally state within possible